Hey everyone, welcome back to another video of a series on the differential equations. Today we will be learning a method called the variation of parameters to solve nonlinear homogeneous differential equations. Without further ado, let's go to our first example. Hey everyone, so this is our first example of today solving differential equations using the variation of parameters. So first things first, as we all know, we would like to write down our superposition principle as usual, which is y equals to yc plus yb, because our method here is pretty similar with using the undetermined coefficients. And so we would like to solve for our homogeneous part, which is r squared minus 5r plus 6 equals to 0, and we would know that this is, if we factor this out, we will get r equals to 2 and r equals to 3, because r minus 3 multiplied by r minus 2. And so for our homogeneous part here, we will get this as c1 e to the 2t, because our independent variable is t here, plus c2 e to the 3t. And let's mark this with our as our second equation, and this will be our first equation for today. And so after solving for the homogeneous part, we would like to solve for the non-homogeneous part using this formula right here. And so this is different with the undetermined coefficients method, because we will have a formula written down here and we will just need to plug in the inputs, which are the y1, y2, w, and also g. W stands for the Wronskian. So our y1 here, our first solution is e to the 2t, and our y2 here, second solution, is e to the 3t. And we have that, so let's just write that one down so we don't forget. Our y1 is that one, and our y2 is e to the 3t. And as for our g, or our g of t here, is our non-homogeneous part, which is 2e to the t. And we still have one more input, which is our Wronskian here. Well, our Wronskian is a determinant of both solutions, which we will write them down here, e to the 2t and e to the 3t. And this will be the derivative of the first solution, which is 2e to the 2t. This is the first derivative of the second solution, 3e to the 3t. And taking the Wronskian here, we will get this as calculating the Wronskian by using the determinant method. We will get here 3e to the 5t minus 2e to the 5t, which gives us e to the 5t. And we have all our inputs here, our y1, y2, g of t, and our Wronskian. We just need to plug in our formula here to get our solution for the non-homogeneous part. So our yp, we don't need to write on the formula because it's written on the top right of the screen. We will have here negative e to the 2t multiplied by the integral of e to the 3t times 2e to the t over the Wronskian, e to the 5t dt, plus y of 2, our second solution, is e to the 3t multiplied by the integral again, which is e to the 2t times 2e to the t over e to the 5t. Multiply everything by dt. And then now we just need to solve our integral parts and multiply them with our variable outside of the integration part. And so by doing so, we can cross out some coefficients inside the integration part. We know that e to the t here times e to the 3t is just e to the 4t. And so let's do that. Let's do it step by step so we don't get confused along the way. And yeah, so e to the 3t times 2 e to the t is just 2 e to the 4t divided by e to the 5t, multiply everything by dt, plus e to the 3t multiplied by the integral of 2e to the 3t over e to the 5t dt. And we can simplify this further, and so we get, what we get inside the integral part is 2e to the negative t times dt plus e to the 3t times the integral. We get here 2e to the negative 2t dt. And so doing this integration for both integral parts are pretty straightforward, because we will get here, what we get here is that 2e to the negative t, we take the integration of it, it's just gonna become negative 2e to the negative t. So we will get here negative e to the 2t times negative 2e to the negative t plus e to the 3t times negative e to the power of negative 2t. And so we will get here, the negative cancels out, so it's 2e to the t plus, or rather minus e to the t. So we will get here e to the t. And this is our solution for the non-homogeneous part. And so we got, and let's label this as our third equation. So what we get here is our second equation and third equation here. And we just need to plug them to our superposition principle, which we wrote down at the start when we start this problem, which is y is equals to the complement plus the particular solution. So let's write down our final solution here. Y is equals to c1 e to the 2t plus c2 e to the 3t plus e to the t. And this is our solution for our general solution to this differential equation by using the variation of parameters method. Hey everyone, this is our second example of solving differential equations using the variation of parameters method. So to start with, we're gonna write the superposition principle, which is y is equals to y of c plus y of b. And let's label this superposition principle as our first equation. And so solving for the homogeneous part, we can write this down as 4r squared minus 4r plus 1 is equals to 0. And solving this, we can use the quadratic formula or completing square, whichever you prefer. I prefer to do with quadratic formula. And 4 plus or minus b squared 16 minus 4 times 1 is another 16. So inside the square is just 0. Divided by 2, 8. 2 times 4 is 8. So we can see here this 1 over 2. We get only one root or one solution, which means we get a repeated root because we have this as a polynomial of degree 2. And so our yc will be c1 e to the 1 over 2t plus c2t e to the 1 over 2t. And so let's label this as our second equation. And so now we're gonna solve this for the non-homogeneous part, which is our yp. And before doing so, we're gonna divide our first equation here that we started, our first differential equation, by 4, because we need to have this what's in front of our second derivative to be a coefficient of multiplied by 1. So dividing it by 4, we get here y double prime minus y prime plus 1 over 4y is equals to 16, actually 4e to the 1 over 2t. And so we're gonna use these equations to solve for the non-homogeneous part. And so we're gonna start by writing down our y of 1 again. Our first solution is e to the 1 over 2t. Our y of 2 is te to the 1 over 2t. And our g of t, our new g of t, is 4e to the 1 over 2t. And so we just need to calculate for our Wronskian using the determinant method. So calculating our Wronskian here is pretty straightforward again, by writing down both of our solutions, e to the 1 over 2t and t e 1 over 2t. Taking the derivative, first derivative, which is straightforward again. And for this one, we should take the derivative using the product rule because we have t and e to the 1 over 2t right there. And so taking the derivative, first derivative, using the product rule will result us in this form. taking the Wronskian, which is the determinant 2 by 2 of 2 by 2 matrix, we will get here e to the 1 over 2t times e to the 1 over 2t plus 1 over 2t e to the 1 over 2t minus, let's write down on the side here so we can all see the process, 1 over 2 t e to the t. Actually, this is just e to the t, because remember we multiply e to the, no, we haven't multiplied that out. Okay, so after we distribute this out and simplify this, we will get e to the t plus 1 over 2 t e to the t minus 1 over 2 t e to the t, which only leaves us with e to the t as our Wronskian. So we have all of our factors here, or all of our inputs that we will be needed to put into the non-homogeneous part formula. And let's write down our non-homogeneous part formula so we don't forget. Yp is equals to negative y1 multiplied by y2 times g of t over the Wronskian, and multiply all of the integral part with d of t plus y2 multiplied by the integral of y of 1 times g of t over the Wronskian, and multiply everything inside by d of t. And so let's plug in our y of 1, y of 2, g of t, and our Wronskian inside this formula so we can solve for it. Negative 1 over 2 e to the 1 over 2t multiplied by the integral of y2 is t e to the 1 over 2t times g of t is just e for e to the 1 over 2t. Divide everything by the Wronskian, which is e to the t, multiply everything inside by d of t plus y of 2, which is t e to the 1 over 2t multiplied by the integral of y of 1 e to the 1 over 2t times g of t, which is 4 e to the 1 over 2t, and divide everything by the Wronskian one more time, e to the t, multiply everything by d of t. And so let's simplify what's inside our integral first before solving our integral, because it makes our life easier by doing that. And so this all equals to negative e to the 1 over 2t multiplied by the integral of, we know that e to the 1 over 2t times e to the 1 over 2t is just e to the t, so we can cross our e to the t out here, and also for this one with our denominator, of course. And so this just leaves us with 4t multiplied by tt plus t e to the 1 over 2t times the integral of 4 dt. Checking if we have made any mistakes, and yeah, we're not. So we continue this further. We're taking the integral of 4t, which is just 2, multiply this by 2t squared plus t e to the 1 over 2t multiplied by 4t, and we get here out for our non-homogeneous solution, or y of b, is 2t squared. Let's write this down as 4t squared e to the 1 over 2t minus 2t squared e to the 1 over 2t, which simplifies to 2t squared e to the 1 over 2t. And so we have here our third equation, or our solution to the non-homogeneous part. We just need to plug in our solution to the homogeneous part and non-homogeneous part back to our superposition principle as what we did in the previous problem. So we have here y. Our final solution will be y is equals to the homogeneous part, which is c1 e to the 1 over 2t, c1 e to the 1 over 2t plus c2 t e to the 1 over 2t plus our solution for the non-homogeneous part, which is 2t squared e to the 1 over 2t. And if you want to simplify this further, you can, but if you don't want to simplify this further, you also can do that. But I like to simplify things, so Let's pull out our e to the 1 over 2t here, and this leaves us with c1 plus c2t plus 2t squared, and we can simplify this further out again by pulling out our t here, and this will becomes c2 plus 2t. And this is our final solution of solving this differential equation using the variation of parameters method.